Okay, so why don't we get started here? So we're finishing up section 10.2 from yesterday, where we left off with some properties of vectors, and now we're going to talk about the standard basis vectors. Okay, so if you've taken DiffyQ before, or you plan to in the future, or maybe even in it now, the word basis kind of talks about what it means as like a building block in the space that you're in, right? So basis just kind of means how can I write anything in the space as a combination of these building blocks, right? Just think of kind of like Legos, right? If I have a certain combination of Legos, I can make, whatever you would want, right? So the basis vectors for R3 are any orthogonal three vectors that we can kind of just, or they actually don't even need to be orthogonal. But what we can do is kind of do a common set of three vectors that allow us to write any vector in R3 by a sum of these three. And we're going to call these I hat, which is 1, 0, 0. We'll also have j hat, 0, 1, 0. And then finally, we'll have k hat, which is 0, 0, 1. So using a combination of these three vectors, we can write any vector in R3. And notice here that these are all unit vectors. They all have length 1, right? It's pretty easy to check their magnitudes, right? We'll just have a magnitude of 1 for each of these. Okay, so for an example, if I have the vector A, B, C, I could write this as the scalar A times I hat plus the scalar B times J hat plus the scalar C times K hat. Right? So that's another form that you'll typically see these vectors written in. Instead of these bracket notations, you'll see them written as the sum of some basis vectors. In this case, we're using I, J, and K hat. Sometimes you might see I, J, and K hat written as X, Y, and Z hat. Typically, the hats kind of represent a unit vector, right? So maybe you're in 4D, and then you'll use some other 4 letters with a hat over there, right? So as long as it kind of denotes the direction we're talking about. In fact, we'll talk about other coordinate systems in R3, and those will also have basis vectors, or commonly used basis vectors. Okay, so now let's do an example, and this is going to be our first big example of the semester. We're going to use vectors to solve this neat little problem here. So imagine here that I've got this roof or some ceiling here, and now I've got a box that's being hung by 2 strings that get attached to the ceiling here. And I have that this box weighs 100, let's use grams. Okay. And now what I can do is I want to figure out the tension in each of these strings, right? So tension, you can think of as having a magnitude, how much of a force is pulling, and then a direction, right? And you can imagine that the tension is going to be pulling along the string, right? So we're going to have some vector. We can kind of even draw a force diagram here. where we'll have a vector that's pointed in this direction, a vector that's pointed in this direction, and then we'll have another vector here that we'll just call capital F. One other piece of information we have is the angle of these strings to the ceiling here. So this one here is 32 degrees, and over here I have 50 degrees. So the goal of this problem is to figure out what the tension is of these strings. So good old classic physics 1 problem, but we're going to use vectors to figure this out. Okay. So let's kind of make that the top there. We need all the room we can get. So the objective is here to find T1 and T2. Well, what I'm going to do is now I'm going to decompose my vectors T2 and T1 in terms of I and j hat, right? So I'll draw a little coordinate system here. Well, I'll have the x direction and the y direction, right? So I'll have an I hat that goes in the x direction, and I'll have a j hat that goes in the y direction here. So let's decompose T2. Okay, so let's decompose T2 in terms of its x and y components. Well, if I look at T2, kind of represents this string here. The x component will be this hypotenuse times the cosine of this angle. Well, what's the length of the hypotenuse of T2? Well, it's just the magnitude of T2. We don't know what it is yet, but we can write it down. This is the magnitude of T2 cosine of 32 degrees I hat, right? So that's my x component. Now for my j component, or this y component, I need to multiply that hypotenuse, or the magnitude of T2, by sine of 32 degrees. And this is in the j hat direction, or the y direction. Okay. So now let's decompose T1. Again here, I'm going to look at the x component first. But we got to be a little bit careful here, right? It's almost going to be the same as this, except we have a T1 here. But we have to keep in mind that now this is pointed in the negative x direction based off of the scheme that we've wrote up here, right? So T1 is pointed in the negative magnitude of T1 cosine of 50 degrees I hat plus the magnitude of T1 times sine of 50 degrees j hat. Okay, so let's put a big old star next to these equations because we're going to have to use these later on as well. Okay, so this is our decomposition. We've turned these vectors T1 and T2 into their decomposition of their x and their y components. Notice we still don't know what the magnitude of these vectors are, but hopefully we'll be able to figure this out. Okay, so let's use some physics knowledge, right? This box is not accelerating. It's going to just stay where it is, just hanging there. Hopefully, doesn't fall. So that means that we know that all of the forces in the x direction and the y direction end up canceling, right? Okay. So we know in vector form that the force of T1 plus the force of T2 equals what we'll call, well, let's put a negative out in front here. This negative F, right? And basically, if you look at this, it's just all three forces added together cancel and equals 0, right? So that's why we have this negative sign out in front of this force here. Okay, well, this isn't this isn't the best way to kind of write this. But what we'll do is, instead of writing, this force as being the gravitational with the constant g, I'm going to, for simplicity, just for simplicity, we're just going to write 100 j hat here. Now, you would have to, multiply our mass times our gravitational constant, but just for simplicity, 100's a nice number. Let's just keep it like that. Okay. So notice that this is j hat, meaning that it's pointed in this should be a negative here. Oh, wait, no. No, that's fine, because this is pointed down and we have a negative out in front. So this is positive. So we have the positive 100j. Okay, so now what we're going to do is, now that we know that T1 plus T2 is this 100 vector, I can sub in these decompositions here. Okay, and I'm going to write it in such a way that I group all of the I hat and all of the j hat. It's 100 because f is already negative. So since f is negative 100, we have this negative, so we end up with the positive here. Okay, so let's keep our star equations. And I'm going to plug those into the equation that I've got there, but I'm going to write it in such a way that I only look at my I and j hat. So I get my negative magnitude of T1 cosine of 50 degrees plus the magnitude of T2 cosine of 32 degrees, and my bracket here, and this is everything with an I hat. Okay, then I'm going to write everything with my j hat. So this is my magnitude of T1 sine of 50 degrees plus the magnitude of T2, there we go, sine of 32 degrees j hat. Let's write that hat a little bit nicer. There we go. So this is the combined x direction, and this is the combined y direction based off of this relationship that we have here. And this is equal to 100 j hat. So from here, what we're going to do is we're going to be able to read off two expressions, because notice that the left and the right hand side of this equal relationship needs to match, right? So the only way for there to be 0 I hat on this side of the equal sign is that this term here is equal to 0. And then the only way for there to be 100j on the right hand side is that this term here is equal to 100. So from that, we get two different relationships. We get that the magnitude of T1, the negative magnitude, T1 cosine of 50 degrees, plus the magnitude of T2 cosine of 32 degrees is equal to 0. And we also have that the magnitude of T1 sine of 50 degrees plus the magnitude of T2, that should be sine of 32 degrees, is equal to 100. Okay, so now all we're looking at here, we've got two equations, and notice that we have two unknowns. I have the magnitude of T1 and the magnitude of T2. Those are my two unknowns here. Great. So let's continue with that. Let's try to solve. Well, if I look at my first expression there, I get that the magnitude of T2, I'm going to solve for T2 here, is the magnitude of T1 multiplied by cosine of 50 degrees over cosine of 32 degrees. Right, that's just from our first equation here. We just move over this term here from the negative, and then we're solving for t2, so we divide by our cosine. Okay, well, now that I have t2, or the magnitude of t2, I'm going to plug that into my second expression here. So we're going to plug it in. So we get magnitude of t1 sine of 50 degrees plus the magnitude of t1 cosine of 50 degrees divided by cosine of 32 degrees multiplied by our sine of 32. So notice all we just did was just plug this relationship into our second equation here. And we knew that this right here was equal to 100. Okay. So now the only thing that we need to solve for here is just t1. So we have that t1, or the magnitude of t1, is equal to 100 divided by sine of 50 degrees plus tangent of 32 degrees. That's what the sine over cosine here is. And then we have a cosine of 50 degrees. So that's all in the denominator there. Okay, so now here's where we might use a calculator. So this is approximately 85.64. Perfect. Okay. So now, based off of this relationship, we now have what the magnitude of t1 is. Well, t2 relies on t1 from our expression up here. So what we'll do is we'll just go ahead and plug that one in. So that means that the magnitude of t2 is approximately 64.91. Okay. We're almost there. So notice that we only solve for the magnitude here, right? We need to actually find out what the vectors are, not just their magnitudes, right? Because we have the magnitude, but we also need a direction. Okay, so what we're going to do is, now that we have these relationships for t1 and t2 in magnitude, let's go back to our star expression, right? Here we are, right? t2, I can write out in I and j form as long as I just plug in the relationship for the magnitude of t2, and the same thing for the tension t1. So we plug these back in. So plug into star, and we'll get that t1 is equal to negative 55.05 I hat plus 65.60 j hat, and I'll get that t2 is 55.05 I hat plus 34.40 j hat. Okay, so that is our final answer. Now, I hope if you take anything away from this course way down the road when you might forget what Calc 3 is all about, always think about how rational your final answer is. Does it make sense? Okay, so take a look at this. we know that the x components we've got here are -55, about, and then a +55. Well, we should know that the box is not moving horizontally, right? It's not moving in the x direction at all. So it makes sense that the forces in the x direction for the tensions are canceling. They're exact opposite of one another because gravitation isn't contributing horizontally at all. So it makes sense, since this box isn't moving, that our x values cancel, right? And if we look at our y values, these add up to 100, right? And that makes sense because it should cancel with the -100 that's going from gravitation down here. Okay, we did it. Right? We solved, this is the hardest example we've done so far, and we've used vectors to do a little bit of physics. Okay, and with that, we finished up 10.2. So let's go ahead and hop to another page here, and we'll start on section 10.3. Okay. Let's go back to the writing tool. We're looking at section now 10.3. And in this section, we'll talk about the dot product. Okay, so notice when we were talking about these like addition and these scalar multiplication of vectors, we didn't really talk about what it means to multiply vectors together, right? In fact, there's multiple ways to kind of define how to do so. And one of these is called the dot product. Okay, so the dot product is defined if we have some vector A, and we'll do this for R3. We have as A1, A2, and A3, and we'll have a vector B, which is B1, B2, and B3. A dot B, so this is how we write the dot product here, is with this little dot here, is equal to A1, B1, plus A2, B2, plus A3, B3. So there's a few big takeaways from this, right? So notice that it's a sum, and each element of the sum is a multiplication of similar entries in the vector, right? So this is A1 and B1, so the first components multiplied together, and then we add the second components multiplied together, and followed by the third components multiplied together, right? Another takeaway from this is that after the dot product has been performed, the thing over here is no longer a vector, right? This is not a vector anymore. I took two vectors, I multiplied them using this dot product, and I got a scalar value out of it, right? And that's a big distinction that we'll see later on, right? So this is a scalar value that comes out of this dot product. Okay, sometimes this is called a scalar product as well, instead of the dot product. But for all intents and purposes, because we're going to use a dot, we're going to call it the dot product. Okay, so more generally, let's say in Rn, So we did this in R3, but in Rn, the dot product of two vectors we can write as the sum from I equals 1 to n of A sub I times B sub I. And that's just a fancy way of saying that we add up all of the element-wise multiplication of these vectors. The first ones get multiplied together, added by the second ones multiplied together, and so on. Okay. So let's do an example where we look at some dot products. Let's do 1, 3, so a vector in R2. And then we're dotting it with 2, -2. Well, this will end up being 1 multiplied by 2. So this is the multiplication of the first entries in these vectors, plus 3 times -2, or the multiplication of the second entries in these vectors. And this will give us a -4. Okay, another dot product, this time we're going to do it in R3, is 2, 1, 6, and we're going to dot it with 4, 7, and -1. So this time we look at the first entries, so 2 multiplied by 4, and we add the second entries multiplied, so 1 times 7, and then we multiply the third entries here, which is our 6 and -1, and this time we end up with a total of 9. Okay, and then we'll do one more. Let's write it in terms of our I hats and j hats and k hats. We have negative I hat plus 3 j hat plus k hat dotted with 2 I hat plus 3 k hat. Okay, so be mindful when you see it in this form, because we can always write these in their bracket notation. So maybe we'll do that up here. This is -1, 3, 1. Always good to get some practice going back and forth between the two. And we have 2. And notice that I don't have a j hat on this vector, which means I have a 0 here. Right? So that's 2, 0, 3. So now when I do this dot product, I get -1 times 2 plus 3 times 0 plus 1 times 3, and that leaves me with a value of 1. Okay, so dot product doesn't seem too bad, right? All I'm doing is just multiplying similar entries and then adding them all up. Okay, so let's talk about some properties. Ooh, those are lines. Don't want lines, just want, yeah, there we go. Okay, so properties. First one here is that if I have A and I dot it with itself, we can write this as the magnitude of A squared. Right? And if you think about the definition of the dot product and what it means to take the magnitude, right? It's the square root of all of those things squared, right? So if I square it, I just get the sum of all of the entries squared. right? Well, that's exactly what it means to take the dot product with itself. And we're going to use this property a lot. Okay, 2, if I have A and I dot it with B, this is the same as if I have B and I dot it with A. So the dot product allows us to rearrange which order we do it in, right? Which is nice. This is a really nice property. And it's not going to hold true for some of the other multiplications of vectors. So now we have here A dotted with the sum of the vector B and the vector C. I can write this as A dotted with B plus A dotted with C. So it's also like a distribution property that we've kind of seen with normal multiplication. Also really nice property. 4 is if I have a scalar, which we'll call D, and it's multiplied on a vector A, and then now I dot this with the vector B, I can write this in 2 different ways. I can write it as D times the dot product of the 2 vectors, or I could write it as the vector A dotted with the quantity of the scalar D times the vector B. So it doesn't matter when we multiply that scalar value. And finally, for now, if we have the 0 vector and we dot it with A, we get the 0 vector back. Oh, no, sorry, just the 0 scalar. Okay, so some cool things is this shares a lot of the same properties of the product of just normal scalar numbers, right? So you can kind of think of these properties as the most fitting type of multiplication in terms of how it behaves like the normal multiplication that we're used to for real numbers instead of these vector entities. Okay, so now I've got a question. I've explained what this dot product is and its definition and some of its properties. But what I haven't done is describe what this means geometrically. If I have these vectors, what does it mean? What does it represent graphically when I take this dot product? For that, let's kind of dive in here. Actually, let's do a new page. So what does it mean graphically here? Ooh, let's do some lines. Let's make a nice little Cartesian. Yeah, okay. Ooh, let's do it for the vectors as well, actually. So if I have my first vector out here, and I have some other vector out here. So these don't need to be in the like YZ plane. They can be wherever. And what I'm going to do is I'm going to draw a vector that goes between them here. And then let's do some drawing. We have some angle that's measured between the two in whatever plane that they share as theta. We'll have this A vector here, and we'll have some B vector here. So first off, let's talk about what this line represents right here. What is this vector? Well, we talked about the parallelogram law last time, and how the parallelogram law is when we added these two vectors, the sum was from them end to end. Well, we can write this guy here as the difference This is A minus B. And that's something we didn't really touch on too much last time, but when we're doing subtractions, so kind of think of what happens when we're adding this negative, right? So in graphical representation, it's connecting the terminal points of our vectors. So now that we've got the three sides of this triangle in R3, what does this dot product kind of represent? Okay. So, and I know you all remember your law of cosines. It's the law of cosines. Says, and that's actually, let's put, so this is the origin, O, the point capital A, and the point capital B. So then we can say that the line segment from A to B squared is equal to the line segment from the origin to A squared plus the line segment from 0 or the origin to B squared minus 2 times the magnitude of the line segment from the origin out to A, and the magnitude of the line segment from the origin to B, cosine theta. And that's without talking about vectors at all, right? That's just the law of cosines. So we can write this in terms of our vectors, though. So let's go ahead. So in terms of our vectors, this is the magnitude of the vector A minus B squared is equal to the magnitude of the vector A squared plus the magnitude of the vector B squared minus 2 times the magnitude of the vector A multiplied by the magnitude of the vector B, and then cosine of the angle between the vectors A and B at theta. Okay. So if we didn't have the dot product yet, we could be stuck here. But I want you to take a good look at this quantity that we have on this left-hand side. So using one of the properties that we just discussed, we said that the magnitude of a vector squared was the same thing as dotting it with itself. So this is A minus B dotted with A minus B. Okay, great. Let's use some other product rule properties, right? If we have, it's almost just like foiling here. We have A dotted with A minus A dotted with B minus B dotted with A plus B dotted with B. Okay, so this first term here is the dot product of A with itself, which we'll rewrite as the magnitude of A squared, right? That was one of the definitions that we talked about. Now, these cross terms, so remember one of the other properties was that the order of the dot product doesn't matter, right? So what I can do is write this as minus 2 times A dotted with B. And then finally, I again have a vector dotted with itself. So this is the magnitude of B squared. Okay. So with that, let's substitute this guy into our expression right here. And notice that if I plug this in, I've got a few like terms. I've got this guy here and this guy here. I also have this one and this one. And those end up canceling, right? So if I plug that in, what I end up with is this -2 a dot b is this -2 magnitude of A, magnitude of B, cosine theta. Well, they both share a -2 in common. So the only terms left is this A dot B is equal to the magnitude of A times the magnitude of B times cosine of theta. And this is another perfectly fine definition of the dot product that we can use. They're equivalent. This is typically what physicists use as their defining definition of the dot product. So what does this kind of tell us about the dot product? Well, imagine that we were using this to solve for this cosine theta. I can say that cosine theta is equal to the dot product of A and B over the magnitude of A and the magnitude of B, right? So this is a way to find the angle between two vectors on the plane that they share, right? So that kind of tells us that the dot product is a method of which to find this angle, right? The dot product can help us convey the angle between two vectors on their shared plane. And that's pretty cool. And we're going to be able to utilize that to figure out a few different things. And with that, we're closing in on today's lecture. So why don't we end it there? We're going to take a 5-minute break, and then we'll start recitations up.